Okay, so we want to make the vector -2, 3 a unit vector. So to make that a unit vector, what should we do first?
Find what the magnitude of v is.
Yeah, we need to find the magnitude, and there's a formula for that. It's not that hard. So v, by the way, again, was -2, 3. So we take the square root of -2. Squared plus 3 squared. You can use a calculator, but hopefully you do this in your head. 3 squared is 9, -2 squared is 4, that's root 13. And let me equation. Okay, so we've now found the magnitude. What do we do with that magnitude? Who remembers?
Divide each component by the magnitude.
Yeah, exactly. We divide each component by the magnitude. So we have -2, 3, and we have root 13. So what we do is, let me pop it into an equation. We're going to have parentheses, and then we're going to have a -2 over the square root of 13. And then comma. And then let me just copy and paste that. I think is easiest. And then copy, paste, and change is a good trick. So instead of -2 over root 13, the second component will be 3 over root 13. And I guess I should call it U for unit vector. I like to use U for unit vector because it's the first letter. Any questions on the first question? Okay, very important to be able to take a vector and turn it into a unit vector. Yeah, that's fine. So maybe I'll fix it because you don't like my parentheses. That's a notation issue. If you want brackets, we can do brackets. It was just easier to do parentheses in the, let's see, that'd be delimiters, I think. Let's even have them. Nope, I'm gonna have to do it this way. Yeah, have to do equation editors. Parentheses are a whole lot easier. But that's technically a little better. Okay, any questions on this? Right, as long as it's clear, like, you know, as long as, you know, in your life you're always using U for a vector. The key is I called it U. If you didn't use U, then it looks like a point. Okay. But let me show you another way of writing it because I didn't do this last time and I want to. We can also write it as follows. Instead of as in that bracket notation, you can say -2 over root 13i plus 3 over root 13j. And that's another way of writing a vector where I represents the vector 0, 1, 0, and j represents the vector 0, 1. And since I don't think I showed you that last time, I figured I'd better this time because that's happens in physics a lot. Any questions on question 1 before we move on to question 2? Okay, let's look at question 2. So we're going to find the distance between the points 2, 5, 1 and -1, 4, 3. Okay. So let me write down. So we have 2, 5, 1, -1, 4, 3. And we need to use the distance formula for that. So if you remember, there was a distance formula, and it's Started with a big square root, a lot of square roots and stuff. And then what you did is it's like the Pythagorean theorem, but now we have 3 instead of 2. So we have -1 minus 2. Squared plus, and then it will be 4 minus 5. Squared, and then plus, and then it'll be 3 minus 1. Squared. Any questions so far? Okay, and now we just do that. I'm just gonna do it in my head. -1 minus 2 is -3. -3 squared is 9. 4 minus 5 is -1. -1 squared is 1. So now we're at 10. And then 3 minus 1 is 2. 2 squared is 4. We're at 14. So it's root 14. Any questions at all on any questions on that? Okay, now let's move on to questions. So now it's a piece of paper piece. Okay. So part A, let me write this down because we have to leave the screen. We have 1, 3, and 2, 1. We're going to take the vector 1, 3, and we're going to subtract 2, 1. And what I want you to do with a picture, because I'm doing it in terms of computing the numbers, that's nothing. But I want to make sure you understand the geometry. And then B was 3, 1, 2. We want to sketch that vector, or sketch that point, sorry. Okay, any questions on the question? Okay, so now I'm going to go over to my document that has a nice sketching tool. And I am going to go to drawing. And let's do the first one. And that is 1, 3 minus 2, 1. So the first thing I'm going to do is I'm just going to draw the axes. And we need some tick marks. Oops. Okay, so the first thing is let's draw the vector 1, 3. Okay, and I know you're supposed to do it by hand, so I'm basically doing it by hand, but I might as well use the arrow key. So that means I'm gonna have to start at the origin, then go over 1, and then up 3. And then I want to draw the vector 2, 1. So I'm gonna start at the origin, I'm gonna go over 2, and go up 1, make a vector out of it. Okay, so now what I need to do, let's see, someone said, shouldn't it be root 15? That was probably for the last problem. I might have added wrong in my head, that's possible. If you want me to look at it, I can. Let me double check. So we have 1, and then let's see, 9, 10, 11, 12, 13, 14. No, I think it's 14. Yep, and Victor agrees too, so I'm gonna go with 14. So that's just an arithmetic thing. You're allowed to use a calculator, by the way. So you can do that if you need to. Yeah, that's okay. I do my arithmetic wrong sometimes too. Okay, the key is if you show your work, then you're gonna get most of the points. If you don't show your work and it's wrong, I give you a 0. And that's awful. So that's just a note, is I do grade on what you've done. It's not just automatic points. Okay, so I want to do the subtraction. How does the subtraction work? How do I make a subtraction? How do I take this vector 1, 3 and subtract the vector 2, 1?
Wouldn't you just subtract the vector components, or?
Mm-hmm. But I need to show a picture. What's a picture going to be is what I'm looking for. I don't want to do any components. I want to look at the picture. What do I draw? Yeah, so what I need to do is I need to take this vector. I need to take the vector 2, 1, and I'm going to put that above. I'm going to put it so that it meets with the other vector. So I'm going to start, let me show you. At the head of the 1, 2, and I'm going to draw that 2, 1 over here, but in the opposite direction. Any questions on that? So then my answer is going to be the completed triangle. Let's make it a bigger weight so we can see it's the answer. Whoops, don't want that one. Let's do that. There we go, and let's make it a bigger weight. And there's the answer. Any questions on the picture? So it's a triangle going on here. So you draw the original, the first vector, you draw the other one from the head going in the opposite direction, but of the same magnitude. And then where you land, that's going to be the subtraction. Okay, now what I want to do is I want to sketch the point 3, 1, 2 in the XYZ space. So let's do that. Again, I'm going to insert a drawing. So the first thing I need to draw is the coordinates, XYZ coordinates. So remember, you do that by drawing these 3 line segments of equal angles. I'm going to label them XYZ. And remember, you always have X to be this left one is X. This right one, I got to put there. This right one is Y. And the top one is Z. Okay, I need some tick marks. I need to get to 3, 2, 1. So let's make 3 tick marks in every direction. Again, I'm not a perfect artist, but I'll do my best. Okay, and now we want to draw 3, 1, 2. So the way I do that, let me use this drawing tool now, or the scribble. And let's make it bigger. Actually, not yet, later. So I'm going to go over from the origin, 3. Yeah, that wasn't very good. One more time. Then I'm going to move in the direction of the y-axis, 1. And then I'm going to go up, 2. Okay, and again, it's hard on the computer to draw it perfectly, so I just do my best. Make the line weight a little bigger so you can really see it. And it's always a good idea if you can, or you should, is to label it. Okay, and maybe make it a point. Any questions on that? There we go.
How do you submit that to Canvas?
So there's a few ways. One is you can save it. I think that the easiest way in this case, since I'm using Google Docs, is I can share it. And yeah, sure, I'll save it as that. And can view. Wait a minute, get shareable link. So if you're using Google Docs, this is the easiest way. And then anyone can view, copy link. So if you're going to do a Google Doc, it's really simple. And then you can just, if you want, you have a choice, you could just paste the link in. Always hit the enter, hit the, the space bar after that, and then it'll make it a link. And then just submit. Does that make sense?
Yes.
Yeah, so if you're using Google Doc, if you got Google Doc, that's definitely the easiest way. And then that shares it, and then I have access because you shared it. One of the things I like about Google Doc is it's really good for sharing stuff. Any other questions about this quiz before we move on? Okay, so let's go to done. There we go. I don't need this anymore. Erase that so I can. There we go. So let us go to definitions of the dot product. Let me ask you, say yes if you have learned about dot products in the past. Some class that you might have had, and no if you haven't. I'm not sure whether they still teach it in pre-calc. I mean, I got it, but that was ages ago. Okay, so so far the first three are saying yes. Okay. So this might be a review for you. So if it's boring, I apologize. I'll do my best. But I want to mention definitions of the dot product. So first thing is I want to talk about why is it plural? Now, do you remember when we talked about the definition of a vector? How many definitions do we have of a vector?
We had two.
We had two. One was with coordinates. The other one was with a picture. And guess what? We're going to have two definitions of dot product because a dot product is a way of multiplying two vectors. Okay? So a dot product is a way of multiplying two vectors. And since a vector can be looked at in component form or in geometric form, they're both relevant. So let me give you a definition of the dot product. I'm going to just call it definition 1. Okay, let V equal, and it doesn't matter whether you go 2 or 3 dimensions. Maybe I'll do 3 so you can get used to it. So how about 3, 1, sorry, A, B, C, and W equal D, E, F. And by the way, we can get away with this because we're not doing calculus yet. So I can use D as a variable, no problem, or as a constant. E also not a problem. Yeah, but we're worried about those for normal things. Then the dot product of V and W is defined by And I think I need to go to insert equation. We're going to have a V and then dot. Let's see if it allows me to dot. Yep. Dot W is equal to AD plus BE plus CF. Okay, and by the way, if it's in R2 and instead of R3, so if it's 2 dimensions, then you just ignore the C and the F. Okay, and if you take linear algebra, you're going to learn that you can do this in 1,000 dimensions. Okay, not a problem. But in our class, we're sticking with 2 dimensions and 3 dimensions. I'm going to give you the 2 and then assume the 3 on this one. You can assume that you can figure out the 2. Any questions at all? Any questions at all on this definition first? Okay, this is very different than, say, addition and subtraction. Okay, what's the main difference that's going to be a big obstacle for us? Here's a question for you. What if I had 3 vectors u, v, and w? How do you define u dot v dot w? Any thoughts? I don't see you all jumping in, but so what if you had a u dot v dot w? Okay, so the problem is you can't. It's not even defined because remember, dot product, kind of the domain of the dot product is a vector and then another vector. So if you tried to do u dot v dot w and did u dot v first, then you're getting a number dotted with a vector, and that doesn't make any sense. Does that make sense? So the big difference between, say, addition and subtraction versus dot product is the result is not a vector. So you're starting this universe of vectors and you're leaving this universe. So it means there's a lot of things you can't do because of that. Is that clear? So a dot product, sometimes they'll call that a scalar product because it gives you a scalar when you're done. But I'm calling it dot product. You often call it an inner product too. There's a lot of words for the same thing. So the biggest problem is you get a number, you don't get a vector when you're done. Any questions on the definition? Okay, very easy to do. I'll do an example, but these examples are simple. I think you'll agree. Once you have the definition, there's nothing to it at all. So let's suppose we have, I don't know, -3, 5, 1. Maybe I'll even do 2 because I didn't do 1 with 2 on the definition, just so you see that it's no big deal. And then dot. And let's say we have 4, 6. And I want to take the dot product. Let's see if you guys can do that. Can you all do that? Maybe you can put the answer in the chat box and see if that's right. It should take more than a few seconds. There's nothing too deep about this. The depth is what we're going to use it for, not the doing it. Okay, so what we do is we take -3 and we multiply it by 4, and we add that to 5 times 6. Well, -3 times 4 is -12. -12 plus 5 times 6. 5 times 6 is 30, and you get 18. There's nothing to it, and that's it. Any questions at all on the definition? Okay. Right now, it's not obvious why we care, but this is actually used all the time. It's really, really important. All right, now let me give you definition 2. Okay, so now let V and W be vectors. Okay. So now notice I'm not giving you components because I want to give you the definition geometrically, which means angle, which means magnitude and direction. Then, and we want to define the dot product. So let me write it out. V dotted with W is equal to, and the idea here is we got to think about what do you have? What do you have in terms of the definition of vectors, the geometric definition? And this is this is what most of you were thinking when we were talking about vectors a couple days ago. When I asked you what is a vector, what 2 things do you have? What is it?
Radius and an angle?
Huh?
A length and an angle?
Yeah, let me give you a little bit better language for that, but you get the idea. A magnitude, that's the word we use for vectors. A magnitude and a direction. So what we can say is that V dot W is equal to the magnitude of V times the magnitude of W times the cosine of the angle between them, which I'm just going to call theta. That's a good letter for angle. Okay, now that's another definition of a dot product. And what I'm not going to do, because we only have so much time, I'm not going to prove that this actually works, that you get the same answer no matter which way. But you can believe me or you can write it out and do it yourself is even better. Any questions on this idea? Okay, so that's a geometric definition of the dot product, and they're both important. They come up a lot. Any questions on that? Okay, so far so good? Okay, so we've got the dot product. Now we want to get into the properties of the dot product. And this is where I'm going to see, because I want to go by the order. They even use I, so I'll do that too. X. Okay, so the first, which is a good thing, and that is, let's write this out. V dotted with W is equal to W dotted with V. Okay. Why is that obvious? Yeah, it turns out it's obvious for 2 reasons. Reason 1 is definition 1, and that is if you switch A, B, and C with D, E, and F in definition 1, then you get the same thing. Is that clear? AD plus BE plus CF is the same as DA plus EB plus FC. The second reason is definition 2. Well, magnitude of V times magnitude W and magnitude of W times magnitude of V, it's the same. And similarly, cosine of the angle between 2 vectors is the same no matter how you order the vectors. And that's because the cosine of theta equals the cosine of negative theta. I don't know if you remember that trig identity, but that was a trig identity, is that the cosine is an even function. Okay, so that's kind of an obvious property from definition 1 and 2. Okay, so by the way, that's the commutativity. Then we're also going to have the distributive property will be true. So let's write that out. And that is, so the distributive property is U dotted with V plus W equals, so what does the distributive property say? That's something you should know just from, 8th grade or something. If the distributive property is true, what should this be equal to? Yeah, U dot V plus U dot W, and it's true. Okay, and again, it's not that hard to show from definition 1 that it works. Okay, the other is the associative property, but with scalar multiplication. And what that says is C times U dotted with V, V dot W. I only want to use U when I have to, is equal to CV dotted with W. And by the way, you can put the C into W if you want also. So that's equal to C dot, V dotted with CW. So that's an associative property. Any questions on that? And the fourth one is that kind of magnitude property, I guess. And that is what happens when you dot a vector with itself. So if we take V dot V, what's another way of saying V dot V? So what's V dot V going to be equal to? Yeah, you got the idea, Eli, but it's the magnitude of V squared. And that, if we use definition of 2, then that's the magnitude of V times the magnitude of V. Well, the angle between V and V is just 0. Cosine of 0 is 1. So that's just the magnitude of V squared. Any questions on that property? Okay, so you could use these anytime you want because they're properties, they're true. What am I using for magnitude symbol? Kind of a double absolute value, and that's standard. Does that make sense? Okay, so that's just what most people use. Okay, any questions about these properties? Okay, we're gonna have other properties, but we're avoiding them now because there's something we're not doing. Okay, what are we not doing this week? It feels really weird in this class, that's a hint.
Calculus?
Yeah, we're not doing any calculus. So it turns out there are calculus properties of the dot product, which I'm not doing. Okay, for example, there's a product rule, which I'm not going to go there, but someday we'll do that. Okay, so those are the properties. All right, so here's a question I have for you. What is the definition of an angle? What's the exact definition of an angle? An
The
angle's
amount of
forever, right?
rotation for something?
What's that?
The amount of rotation that something experiences?
What's that mean?
I'm
It's using
not
another
sure.
word, but if you don't know what that word is, that doesn't help. Right? How do you get a number out of it, right? Okay, and the idea is you have rotation from a fixed point, but what does that mean? If your angle is 0.3, what does that really mean in terms of rotation? Does that make sense? So the reason why this is a tough one is that you've never really learned this. All you did is get an intuitive idea of angle, but you actually never had a true formal definition. But here's the formal definition of angle. And it's really easy if you use definition 2. Okay, so the definition of angle is the angle between two vectors is, well, we just do it. So I need an equation and I need a division. So we go ahead and look at definition 2. That's just going to be V. It's going to be, sorry, it's going to be a little bit more before definition 2. You're going to have the cosine inverse of V, one more there, V dotted with W over the magnitude of V times the magnitude of W. Maybe I'll put some parentheses there to make it a little prettier. And let's make it bigger. And maybe I'll even give it a letter. If you can give an angle a letter, what do you think that letters probably should be? Hopefully y'all know. Theta. That's what most people call an angle. And let's make it a lot bigger. This is actually a definition of an angle. Okay. And you can see why you didn't learn this in 8th grade. Way too hard. But it's not that hard once you get into it. Okay, and now we actually have a definition. You give me two vectors, I can give you the angle between them. Okay, and you can give me the two vectors as coordinates, and then it's very simple. We got a nice definition. Any questions at all on what an angle is? Okay, well that gets us to the next definition. What is the most important, special, easiest angle there is in the world?
Zero?
Yeah, 0. Okay, and hopefully you know that. 0 is a nice, easy number. I don't understand why it was one of the last numbers invented by the human race, but for some reason it was. Fractions happened before 0. I don't know why. Okay, so we're going to be pretending that 0 is actually an easy number, because I think it is. And that is definition is that V and W are called orthogonal. If, okay, well, let's think about this. Let me make this all a little prettier. Okay, so if theta is 0, but if theta is 0, that means that the cosine of theta is 0, right? Well, if the cosine of theta is 0, then what do you know? Theta is 1. Cosine of 1 is not 0. Cosine of pi over 2 is 0. Right angle, right? So orthogonal is the same as being a right angle. Any questions on that? So we want a right angle out of this. So to be a right angle, that means actually theta is not going to be 0, it's going to be pi over 2. It's kind of a nice one if you think about triangles. That means that the inside must be 0. So for the inside to be 0, that means v dot w equals 0. So if v dot w is equal to 0, then we're going to call v and w orthogonal. Any questions on this definition? Okay. Kind of visually, we're talking about right angles. So if you have a right angle, then orthogonal. But again, what does that mean? Well, now we have a definition. What that means in our definition is that v dot w equals 0. Very easy to test if you have a right angle. Let's give you an example. Consider the triangle with coordinates 1, 3, 1, -2, 4, 5, and 0, 1, 0. Is this a right triangle? How do you decide if this is a right triangle using our definition of orthogonal? What do you think? Any thoughts? We find theta, but we don't have to find theta. All we do is take dot products of the vectors, but you got to find the vectors. These are points, not vectors. So to find the vectors, you subtract. So what we're going to do is let's take the first 2 and the last 2. So 1 minus -2 is -3, comma, 3 minus 4 is -1, comma, and then 1 minus 5 is -4. And then we're going to dot that. And now we do the same thing. I'm going to subtract 2 other points. So 0 minus -2 is 2, comma, 1 minus 4 is -3, comma, 0 minus 5 is -5. You get 0 when you do this. I didn't make a mistake. Let's see. 1. The first one. So the first one is -2 minus 1 is -3. Yeah, so I do the second minus the first. Okay, and for the second vector, I do the third minus the second. Well, what is that dot product? It's -6. And then +3. And then +20. And is that 0? Not 0. Okay, we're not done yet. What we just found out is at least that angle is not a right angle. Is that clear? How many angles are there in a triangle, by the way?
3.
You better know. Yeah, there's 3. So I just did one of them. I'm not going to do the other 2 because we only have so much time. But that was to do one of them. I did, vector 0.2 minus 1 dotted with 0.3 minus 2. I could do, say, 0.3 minus 1 dotted with 3 minus 2. See what that is. And then I can do the third one also.
Out of kitchen.
Any questions on that?
Good boy.
Okay, so let's see, I'm looking at time and I got to be careful. I think I'm going to let you read through the projection. So I'm going to lead through, we got 10 different things to do and none of them are that hard, so it's not hard to read. But work I want to do because that's some physics that you might have seen and we've done work before. So if you think about work is kind of like how much energy in a way does it take? Work and energy are directly related, by the way. And I'm a bike rider. In fact, I'm thinking about doing the lake on Saturday. And if there's wind, then you got to think about how much work do you have to do against the wind. But knowing how strong the wind is, how fast the wind is, like whether it's 40 mile an hour, or 10 mile an hour, that's not enough. What else do you have to know? Besides how fast the wind is moving. Yeah, are you going against the wind? Are you going with the wind? Or is the wind just going across? If you're going against the wind, then you're going to have to do a lot of work. If the wind is going across, you're not doing any work against the wind. So the idea is it has everything to do with magnitude, okay, and the direction. Well, those are vectors, but it's your magnitude and direction, the wind's magnitude and direction. So the work done by going along a vector v against a force F. By the way, is a force a vector?
Yes.
Yes, because it has magnitude and direction. Is defined by, let's write it out. Oops, what just happened? There we go. Work is equal to F dotted with V. And that's the definition. I don't think I need to do much about it because it's not, you know the force and you know the vector, you dot them. Okay, any questions on that? And a vector means going from one position to another. So I'm thinking of a vector as 2 points, right? The tail and the head. To go from the tail to the head along a constant force. Okay, by the way, any guess on what you're going to have to do if the force is not constant? If you're going from one place to another, but the wind's changing. Yeah, then you have to do an integral, but it's an integral we don't know how to do yet. That's going to happen next quarter. Just to let you know. So I like to give you a heads up on, why we still don't really know what work is, because right now we're assuming F is constant. Otherwise, we don't even know how to do this. Any questions on this so far? All right, so what we just talked about is dot product. Now the dot product, what it does, it allows us to take two vectors and multiply them. But the issue, okay, the downfall of that, remember what the problem was with the dot product? Thinking of it as a multiplication.
You can only do two?
You can only do two, but even worse, what do you get when you do a dot product? You start with two vectors, do you get a vector? You don't get a vector. So you leave your universe when you do a dot product. So what we want to do is we want to find a different product, a different definition of product, where you're not leaving your universe, where you're taking a vector, you're multiplying by another vector, and you get a vector, because that's better, isn't it? That's how it should be with multiplication. Okay, well, here's the definition. Today's a lot of definition days. And that is let V and W be vectors in R3. Then the cross product of V and W is defined by, and this one's a bit messy, V cross, I think I need to do this kind of cross. Let's see if it allows me. There it is. V cross W is equal to the determinant. Haven't played determinants. All right, so I may have to just kind of explain then. The determinant of the matrix and what we're going to do is we're going to write IJK and then the first row will be, I'm going to call it A, B, C, and then the third row will be D, E, F. Where V is equal to the vector ABC, and W is equal to the vector DEF. All right, so let me ask you, give me a yes if you've seen determinants of matrices. Give me a no if you haven't seen them. In your chat box. There's 18 of you, well, there's 17 of you, so there should be 17 yeses and nos. Okay. If you had pre-calculus in LTCC, it's a yes, by the way. Or it's a no because you did, but you have no memory of it. But we do it at LTCC. I don't think they do it at South Tahoe High School. I'm not sure. My daughter didn't, at least. But that was a lot of years ago. Okay, some of you don't remember. Okay, so let me remind you what the determinant is. So the determinant of the matrix, okay, is the following. So the first thing is what I'm going to do. South High School still does not teach it. That's too bad. Okay, is I'm going to look at the I. I is a vector, by the way. I is a vector 1, 0, 0. And then I'm going to get rid of that, the row with I and the column with I. I'm going to cross BF minus CE. So I'm going to go BF minus CE I. And then I'm going to subtract doing the same thing with the J. That was supposed to be IJ. So I'm going to subtract doing the same thing with the J. So I'm going to go minus, so I'm going to cross the first row out and the second column out, and you get AF minus CD. J. And then I'm going to add the same thing with the K. So I'm going to I'm going to get rid of the first row and third column, and you get AE minus BD. Okay. And that's the definition of the cross product. Okay, it's kind of a weird looking definition. And what's the issue about this one? Remember, the issue was about the dot product was that you don't get a vector when you're done. Here you get a vector when we're done. There's a vector, by the way. You know what the issue is? It's in the definition. Yeah, it only works in 3D. You can't cross two vectors in R2. Just doesn't work. Okay, or again, we're not doing it in this class, but it's really important, and that is higher dimensions. It just doesn't work. This only works in R3. So that's the main issue with the cross product, is you can only do this in R3. But it's nice in R3 because it gives us a vector when we're done. So it feels more like multiplication. Whereas dot product doesn't give you a vector, and multiplication, you should get a vector when you're done, right? I mean, you should have to leave your universe. Is that clear? Okay. Well, there's another definition. Okay. What do you think the other definition's going to be all about? What do you think? Here's a hint. There's two definitions of vectors. Yeah, it's all going to be all about magnitude and direction. And it's really, really important. So, definition 2. I don't think I wrote 1 on here, and I probably should have. So the idea here is that we're crossing two vectors, and we're supposed to get a vector. Unlike getting a number, a vector, you have to describe what the magnitude is and what the direction is. Okay, so the cross product of two vectors, V and W, has magnitude. So let me write this down. Magnitude of V cross W is equal to, well, it turns out it's real similar to the dot product. You remember the dot product was the magnitude of V times the magnitude of W? And then what was it times if it was dot product? Who remembers? Yeah, it was a cosine of theta. Well, guess what? This is cross product, so it's got to be different. It's the sine of theta. It's going to be the times the sine of the angle between the two of them. Okay, any questions on that? Okay, so that's good, but here's better. Okay, so we're not done yet because we've just defined what the magnitude is. What do we have to define? We have this vector called the cross product. We know its magnitude. What else do we have to know? Yeah, we have to know its direction. Angle doesn't quite work because there isn't an angle in R3. There's a direction. So, and the direction of the cross product is orthogonal to both V and W. Let me ask you, is that enough to know exactly what this vector is? What do you think? Okay. Any other thoughts? Okay, it turns out it's not enough. What's wrong? We need to know something else. If I tell you that that we have a vector orthogonal to both V and W, do I know its exact direction? Think about, I don't know if you're looking at a table right now, and if I told you I have a vector that's orthogonal to the table that you're looking at, do you know where it points? You don't, because it might point up and it might point down. Does that make sense? So we need a little bit more. And follows the right-hand rule. I don't know if you remember last time I talked about the right-hand rule. You take your right hand, you grab, and you rotate from V to W, in this case, in order, and your thumb should point in the direction of the answer. So then you know that it's up or down, depending on what V and W look like. Any questions at all on this definition? Okay, so I'll tell you, I think the direction part is the most important and useful part of the cross product. Let me give you an example. Is find a vector orthogonal to both 2, 1, -3 and 3, -1, 1. Well, how do you think you want to find a vector that's orthogonal to both of those? What can we do? Any thoughts? So if we want a vector orthogonal to both of these two vectors, yeah, we take the cross product. Okay, and by the way, if you don't know the cross product, this is a very hard question to answer. Just really messy algebra. But with the cross product, it's actually quite easy. So I'm going to go I, J, K. Whoops. Let's make this next page. There we go. So I'm going to go I, J, K, and then 2, and then 1, -3, and then 3, -1, 1. So now I just do it. So for the I component, I'm going to have 1 times 1 minus -3 times -1, and that's -2. And then we're going to have a minus, because now we're going to do the J component. And we're going to have 2 times 1, that's 2, minus -3 times 3, that gives you 11. So minus 11 J. And for the K component, you'll have 2 times -1, and then you'll have 1 times 3. 2 times -1 minus 1 times 3 is -5. Minus 5 K. And if you want to write in pointy bracket notations, that's -2, comma, -11, comma, -5. Okay. By the way, what's the easiest way of checking your work to make sure you got it right? Let's say this is a test, and you got 1 minute left in the test, and you want to make sure it's right. Maybe 2 minutes left. What might you do? Thoughts? I don't see you all jumping in. But if you want to find out if it's orthogonal, you take a dot product. So I'm going to do -2, -11, -5, dot 2, 1, -3, and I get 0. And then I'm going to do -2, -11, -5, dot with 3, -1, 1, and I also get 0. Okay. And again, you can write it out and see, but we only have so much time. Any questions at all on this example of finding a cross product and saying, aha, we have a vector orthogonal to both. We know the dot product to each of our cross product. Each of these must be 0. Any questions on this idea? Okay, so some things, again, I don't have time to do everything. That it was kind of ambitious to say we're going to be 10 things, but none of this is too hard. So we talked about the definition of the cross product. I want to talk about kind of all the properties, but some of them. Well, with the dot product, we had v dot w equals w dot v. Do you think that's going to be true for the cross? Okay, the answer is no. But what we can say is that v cross w is equal to negative w cross v. Okay, I don't have time to prove it, but it's not that hard to prove. You just do it. So it says that this is not commutative. This is anti-commutative, they call it. Anti because you have a negative sign. Any questions at all about the cross product and anti-commutativity? Okay. I'm just going to say a few things. The distributive property does work. So U cross V plus W is U cross V plus U cross W. So that's definitely true. Another one that's really important, so I'm going to write down the kind of the ones that may not be obvious, but they're really important. One is anti-commutativity. The other is V cross V. What is that? What must it be? Any thoughts? Jumping in, so I'm just going to say it. It's always 0. And it's not the number 0, it's the 0 vector. Okay, and that's because if you have V cross V, the angle between V and V is 0, right? And the sine of 0 is 0. So V cross V is 0. Okay, so that's always true. Okay. Is that clear? Okay, so I want to give you those, and I'll let you look in the book for the ones that are kind of more like, yeah, that should be true. But these two are not as obvious right away, and they're useful. Okay, little geometry. Okay, one is that the magnitude of the cross product is equal
To figure out.
to the area of the parallelogram. When I say parallelogram, what do I mean?
Come on, someone.
So here's a V, and maybe here's a W. How do I get a parallelogram out of this? Yeah, tip to tail. So I look at V plus W. That's better. Okay, so if I take the area of this parallelogram, that's V cross W. There we go. Any questions on this? Let me see them close. Here it is. Any questions?
Is it always having the like, so there's the V and the W. Is it always having the arrows face in that other direction when you're finding a parallelogram, or can it be the opposite direction?
So you're making a parallelogram out of it. I could do a different one. Let me go grab one. I think it's having some issues here with the computer. Sorry. Let's try that. Nope. Save and close didn't work, and now I'm frozen. Try this. No, that didn't work. Let me do this. Sorry, but I think I have to do it without sharing because it's dying on the sharing thing. Oh, still dying. Sorry about that. Ran into technical difficulty. When I have the Zoom and the screen open at the same time, things happen with hitting things on top of each other. So sorry. All right, let me reshare. Okay, so the idea, what your question was, and let me go find, let me go grab it. So if you had a V like this, and you could have a W in the other direction, is that what you mean, like over there somewhere? So you always place them so the tails are connected. Maybe that answers your question. I'm not exactly sure what your question is. So if you had that, then we go ahead and we connect this way. And I'm not a perfect artist, but that's supposed to be a parallelogram. Just a note, what if we wanted, instead of that, we don't want the parallelogram, what if we wanted a triangle? How do you find the area of a triangle? Using the cross product. And where is it? Yeah, you get their idea, but not star, it's cross. So the area of the triangle is 1/2 triangle is 1/2 V cross W. And it should be magnitude. Any questions on that? And that's because a triangle is half a parallelogram. So nothing too magical there. Okay, final thing, I only have a minute, but that is, we can talk about parallelepiped. Parallelepiped. There we go. All right, so you know what a parallelogram is? That means in 2 dimensions, you have 2 vectors, and you make a parallelogram out of it. But a parallelepiped is the same idea in 3 dimensions. It's kind of like a parallelogrammy box. And the volume of the parallelepiped with vectors U, V, and W is U, right back here, U dotted with V cross W. So what's cool about this is it puts everything together, dot product and cross product. And that gives you the volume of the parallelepiped with vectors U, V, and W. So think about a rectangular solid. You need to know up, down, left, right, and forward, backwards. Well, here you have to know the same thing, but now they may not be right angles. So they're just random 3 vectors. And that's how you find the volume. And notice V cross W is a vector. So you're taking U dot a vector and you get a number, and that's good. Okay. And I believe actually it's a little more than that. It's the absolute value of that. Because it has to be a positive number. So we're out of time. I am going to stop my share and stop the recording.